Types of aqueous solutions. So let's think about two familiar solutions, salt water and sugar water. You can imagine doing this at home. You put a teaspoon of salt into a cup of water and a teaspoon of sugar into a cup of water, and you stir them up, right? And it seems like the salt and the sugar disappear. These are solutions. The salt is mixed thoroughly with the water, and the sugar is mixed thoroughly with the water. You taste the sugar water, don't taste the salt water, it's nasty. Taste the sugar water, the very top, the very bottom, it all tastes the same. It's sweet, right? How do those things dissolve? When we do stuff like this all the time, you're making pasta and you salt the water, we don't stop and think about, I just made a solid disappear into a liquid. How does that happen? That's kind of weird, isn't it? So how does that happen? There are attractive forces that hold particles together, and we're going to learn what those are later. For now, we're just going to talk about them generically. There are attractions between the solute particles. So in that cup of water, the reason that the water is a liquid and sitting in the cup and behaving itself instead of flying off as a gas is because the water molecules are attracted to each other. And the reason the salt stays in the salt shaker and doesn't float out through the holes as a gas is that it's got attractive forces between the ions. And so the solute particles have attractions, the solvent particles have attractions for each other. When we mix these two things together, we also have the potential for solvent-solute interactions. And in order for something to dissolve, we have to have a correct balance of these. We can't have one that's super strong and others that are really weak. We have to have the right combination of attractive forces. So, in a water molecule, we have covalent bonds. We have oxygen, which is a nonmetal, and hydrogen is a nonmetal. And so they make a bond by sharing electrons. It does not form an ion. When you share something, though, you can share it evenly or you can share it unevenly. You ever shared a bed with someone? What am I going to talk about? The blanket, right? There's always someone that's hogging the blanket. It's like, yeah, you shared the bed, but it wasn't shared equally. You were out in the cold. You only had a blanket over, one leg, and they were all toasty and warm. That's what happens here when oxygen and hydrogen share the electrons. Oxygen's a blanket hog. So it has the electrons more than the hydrogen does. And so that makes the oxygen a little bit negative because it's got the electrons more, and it makes the hydrogen a little bit positive. It's not an ion. It's not a +1 and a -1 charge. This might be -1/8 or a 10th or something. It's just a little bit, but it's still something. And so this is the Greek letter delta, lowercase delta. It kind of looks like a lowercase d with a posture problem. Slumping, maybe you've been looking at his cell phone too long. That means partial negative charge, and this is partial positive charge. So that's what happens in a water molecule. So when we put sodium chloride into the water, sodium chloride has actual ions, positive ions and negative ions. The negative end of the water molecule is going to be attracted to the positive ion. And the positive end of the water molecule is attracted to the negative ion. Does that make sense? Now, this is just a partial negative charge. Can one water molecule replace the attraction of this full -1 ion? No, it can't. But there's more than one water molecule. So what we find is that this sodium ion is going to be surrounded by a number of water molecules. And together, their partial charges will replace the attraction it felt for the other ions. And for the chlorine, water can do the same thing, because water's like one of those two-faced friends, right? And they'll act this way with one group of people, and they'll act completely the opposite with another group of people, right? So here is like, ooh, here, see my negative side. And over, ooh, here, see my positive side, right? So it can be either. Another very non-politically correct way to think about this is, so you have these little positive and negative ions here. They're like little children in a group school outing or something, and the water molecules are these evil people, and they come and they lure them away. It's really bad, isn't it?
It's terrifying.
I know, it's terrifying. But you'll remember. I'm not advocating doing that by any means, but
So if we don't have enough water to lure the children away, then the salt's just gonna.
yeah, it's interesting because somebody asked that question yesterday too. Well, what if you don't have enough water molecules to, surround all of these ions? Well, then they won't all dissolve. Yeah. So in this solution now, I have this positive ion that's surrounded by the water molecules, and that can float around. And these negative ions surrounded by water molecules, they can float around. They can move in the water. So I have charged particles that can move. This solution is able to conduct electricity. Electricity is a flow of electrons. And so in order for electricity to flow through a solution, there has to be something that can carry the charge. And here it's the ions. So we call a solution that can conduct electricity an electrolyte. So this is the conductivity apparatus. And here I have a beaker with deionized water in it. And I have 2 electrodes here, and these are connected to a battery and a light bulb. If I touch the electrodes or put a wire between them, I complete the circuit and electricity flows and the light bulb glows. But if it's just in pure water, it can't conduct the electricity, and so nothing happens. If I put salt into the water and dissolve it, then the light bulb starts to glow, because the salt solution conducts electricity. So we call that an electrolyte. Soluble ionic compounds are electrolytes. They dissolve, the soluble, and they form ions. So where do you hear the word electrolyte in everyday life? Gatorade. Yep. Let's not forget Powerade. Why do they say you need to drink Gatorade? To replace your electrolytes. What are those and how did you lose them? Sweat. When you sweat, there's water, of course, that comes out, but there are also small amounts of salts, not just sodium chloride, but other salts, electrolytes, that your body uses. There's a lot of electrical stuff that goes on in your body, and there's a lot of processes that depend on the correct balance between sodium and potassium levels and other ions. When you sweat a great deal, you lose a significant amount of salt. My husband used to go golfing. He doesn't have time anymore, but he'd go out in August, his black hair and a dark shirt. It's 106, and he's out in the sun, and he says, oh, that was great. He comes home, and by the time he gets home, his shirt has dried off, and there's like these white lines on it, right? What the heck? It's salt. He sweated out a lot of salts, and then when the liquid dries, the salt is left behind on the dark t-shirt, and you can see it. So, my boys play football, all 5 of them play tackle football, or did, and, they go out and they're in full pads, and it's 105. They sweat. I mean, he is soaked through, like in the first half hour. So does he need Gatorade? Yeah, probably. When I take the dog for a walk and they get all sweaty, do I need Gatorade? Nah, I did not lose that many electrolytes. I can get that back just in eating some food. What I just need is to replace the water. So most of the time, just drinking water is better. And actually, the football players, what they do is they drink Pedialyte, because Pedialyte is made for, children or other people that are having, diarrhea and stuff and losing electrolytes. Because what you really need is the salt. You really don't need all the sugar in the Gatorade. That makes it taste better. But it also kind of dehydrates you because your body needs water to process the sugar. So they'll drink Pedialyte.
I'm an athletic trainer, so
Mhm.
I work with athletes, and if a kid is cramping, we don't give them Gatorade because, like you said, it's too much sugar. We literally have little packets. They're called Gatorlights.
Mm.
You can put them in Gatorade because they taste really bad,
Mhm.
but it's basically like pure salt.
Yeah.
And we make it like make them dump it in their mouth and swallow it with water because it just
Yeah.
gives them like a crazy
Yeah.
amount of salt all at once.
Yeah.
They taste really awful. Though.
Yeah, they do taste awful.
It's just-
Because things that are good for you often don't taste good. And the Pedialyte doesn't taste good. But they've recognized if I drink a bottle of Pedialyte before the football game, I'm much less likely to end up on the middle of the field writhing in pain with a cramp and everyone in the stands wondering if I've blown out my knee. Yeah. So, electrolytes. Then there are non-electrolytes. Well, non-electrolytes do not conduct electricity. So these do not form ions. So these would be most molecular compounds like sugar. So here we have an illustration of what happens if you put sugar into the water. Sugar doesn't form ions. It does not cause the light bulb to glow. Now, does that mean that you don't need sugar? Well, no, we need a certain amount of sugars, but Gatorade has way too much sugar in it. That's why it tastes okay. So salt solutions conduct electricity, sugar solutions do not. Any questions?
So this DI water is then non-conductive, or is this
Right.
And theoretically?
Yeah, so DI water, the purity of it is actually measured in megaohms,
Okay.
which is the resistance to electric current.
Okay.
And so the purer the water, the higher the resistance. Tap water has dissolved minerals in it. Now, is it an electrolyte solution? No, but it does have enough that it will conduct electricity a little bit. So if you take a 9-volt battery and put it in a cup of tap water and wait a little bit, you'll see little tiny bubbles because electricity is flowing from one terminal to the other, gradually discharging your battery, and it's decomposing water, it's electrolyzing water into hydrogen and oxygen, and those are the bubbles you see. And those dissolved minerals, which are ionic compounds, are responsible for a lot of the taste of water. If you taste distilled water, it's not quite right. It's like, what? Some tap water tastes really good, some tap water tastes really awful. Bottled waters have different tastes, and then there's some cities where their water's just, whoa, can't even drink it.
We were evil on the boat.
Yeah?
We give DI water to newbies. So my question is, what makes you puke?
With DI water? That's interesting. I've never really, I've never drunk enough DI water to make myself puke. I have had students ask me, well, is it safe to drink distilled water? Like, well, in the short term, it's not going to harm you, but I would not recommend it because your body needs a certain amount of minerals, right? And if you're drinking DI water, that's going to pull the minerals out. Just like if you drink salt water, ocean water, that pulls the water out of your body and causes you to be dehydrated. So that's interesting that you can drink enough DI water to make people puke. Yeah, well, if you're on a submarine, you got to do something to pass the time, right? So this is what it looks like when sugar dissolves in water. So sugar, as we can see from this space-filling model, has a lot of hydrogens and oxygens. And those hydrogens and oxygens are unequally sharing their electrons, just like the water molecules are. And so the oxygen end of water is attracted to the hydrogens here, and the hydrogen is attracted to the oxygens. And so the water molecules will come around and replace the interactions that the sugar molecule had with its neighbors in the sugar crystal and cause the molecules to separate and float around in the water. But there aren't any ions here, so it doesn't conduct electricity. Any questions? Mm-hmm.
So when you mix an acid with DI water, what happens to the remaining charge, right? 'Cause the ion would be either positive or negative.
Well, that's a good question. So what happens when you put an acid into deionized water? Actually, the same thing happens as when you put it into regular water. The hydrogen ion from the acid actually is too small to be hanging out by itself, so it rides on one of the water molecules and forms this hydronium ion. And then the chloride ion is left hanging around, and so we still have an equal amount of positive and negative charge.
So that could be the reason why deionized water would cause you to throw up, because you have excess chlorine in your stomach.
Possibly. Yeah, I mean, that would be, that's more into the biology, which I know nothing about.
Sounds like an experiment.
It does sound like an experiment. Who wants to volunteer?
I volunteer.
But yeah, so these are the sorts of questions that, cause us to learn about stuff. In this day and age, most of the questions we come up with, someone else has already thought up and figured out. So we don't get to figure it out, but we can just look it up. So we could probably look that up and find out why that is. So acids are molecular compounds, but they ionize when they dissolve in water. So they form ions that were not there before. They form hydrogen ions and a corresponding anion. So the molecules become pulled apart by their attraction for water. So hydrochloric acid is a strong acid. It ionizes completely. That means that all of the HCl molecules get pulled apart. They don't have enough attraction for each other to hang on to each other. They get pulled apart. And so we just have the hydrogen ions and the chloride ions. There are also weak acids. In weak acids, they do not ionize completely. So hydrofluoric acid, some of the molecules will ionize, but many of them will remain intact molecules. Acetic acid is also a weak acid. So here we see that there are intact acetic acid molecules, and there are hydrogen ions and acetate ions. So in a weak acid, we only have a few ions. In a strong acid, we have lots of ions. So a strong acid is a strong electrolyte, and a weak acid is a weak electrolyte because it doesn't form as many ions. So strong electrolytes dissolve completely into ions. Sodium chloride is an example. So all soluble ionic compounds are strong electrolytes. These conduct electricity well. That light bulb has a good strong light, right? So soluble ionic compounds and strong acids. We'll talk about which ones are the strong acids. There's only 6 of them. Weak electrolytes dissolve mostly as molecules, but partially as ions. So these, for the most part, in Chem 1A are just weak acids. They will conduct electricity, but only weakly. And then there are the non-electrolytes like sugar that don't make any ions. Mm-hmm.
So the idea of like a strong acid is not the connection between the ions are not strong.
Right.
It's like the reaction is strong.
So yeah, the idea with strong and weak.
Right.
So one common misconception is a strong acid is more dangerous, right? And a weak acid is less dangerous. No, it has nothing to do with it. It's how strongly does it conduct electricity? How many ions get formed? So a strong acid actually falls apart in water and forms ions very easily, whereas a weak acid, in a sense, the attraction between the hydrogen ions and the rest of the molecule is stronger, and so it stays together. but then you get into this opposite business. So I prefer not to think about that and just to focus on it's a strong electrolyte or a weak electrolyte. So here we see this is a strong electrolyte, and so we get good conduction. The light bulb is strong. And here's the weak electrolyte, and the light bulb is on, but the light is very weak, right? Because the acetic acid doesn't form as many ions, so it can't conduct electricity as well. Over here with the sugar, we get nothing, because it doesn't form any ions. The electricity cannot pass. Any questions? So which of these aqueous solutions conducts electricity? Well, what kinds of things can form electrolytes? Metals in the form of ionic compounds, right? And acids. So what we're doing is we're going to look at this and say, well, is this an ionic compound? Is it an acid? Or is it a molecular compound? So this first one, KBr, is that ionic? Yes, it is, because potassium's a metal and bromine's a nonmetal. So will this conduct electricity? Sure. What about this one? Are there any metals in it? No. Is it an acid? How do we tell? If it was an acid, the first letter would be hydrogen. This has hydrogens in it, but it's not an acid because it doesn't have an H at the beginning. So that's a molecular compound. Here's another one. It's all nonmetals. It's got a hydrogen at the end. Does that make it an acid? No, the hydrogen has to be at the beginning. Here, the hydrogen is put at the end because this OH tells me this is an alcohol. But that's not going to conduct electricity. So ionic compounds and acids can conduct electricity. Do all ionic compounds dissolve in water? No. No, they don't. Which is good because if they did, then all the minerals in the crust of the earth would all dissolve in the water and we wouldn't be left with much. So when an ionic compound dissolves, it separates into ions, but not all ionic compounds will dissolve. And so which ones do and which ones don't? It's complicated. So we can use general terms, soluble and insoluble. Soluble means it will dissolve. Insoluble means it will not dissolve. But as with most things in life, it's not that black and white. Even an insoluble compound dissolves a tiny bit. And you'll learn a lot more about this in Chem 1B. But something like silver chloride, which is considered to be insoluble, you put some silver chloride into some water and stir it up, and you can stir and heat and do whatever you want. It's not going to dissolve. You look at it, it's still just all there. Bless you. Does that mean that no silver and chloride ions dissolved? No. It means that the number that did dissolve were so small compared to how many there are that it's just completely insignificant. So if you had 3 gazillion sodium chloride units and 100 of them dissolved, would that be significant? No. So that's just a little bit of truth. Even the insoluble ones dissolve a tiny bit. So ionic compounds already have ions. So when they dissolve and separate, we don't say they ionize, we say they dissociate. Because ionizing means it forms ions. So this is dissociation. They're just disassociating from each other. So if we have sodium sulfide, remember in Chem 1A, all ionic compounds have 2 ions. And so this is going to separate into 2 ions, and you would do that in the same way that we did when we were learning to name them. We have 1 cation and 1 anion. The metal typically is all by itself, and then whatever's left is the other one. Na2 is not an Na2 2+ ion, it's an Na+ ion, and this 2 tells me there's 2 of them. And it's needed to balance the 2- charge on the sulfur. So if I write an equation showing how this separates into ions, I'm going to get 2 sodium ions and one sulfur ion. If your compound contains polyatomic ions, when a compound like this dissolves, the ions dissociate, the sodium ions separate from the sulfate ions. The sulfate ions are still intact. They're just separating from the sodium. And that's why they have a special name, because they tend to stay together. And so they need a name of their own. So this one dissolving, I'm going to get 2 sodium ions again because it's Na2. And this SO4 is 1 ion. I'm not going to say it's S and 4 O's. And if it was more than 1 sulfate, there'd be parentheses and a number on the outside. So there's just the 1 sulfate. If we put silver nitrate into some water, it will dissolve, all the ions will separate. If we put silver chloride in water, nothing happens. The silver ions and the chloride ions like each other too much, and they're not going to be tricked by the water. So how do we know? There's a lot of factors, and it's not easy to predict. So it's not even worth trying to explain why this one does and that one doesn't. It's very complicated. The best approach is empirical. And so people have done this, and we just use the benefit of what they've learned. They would take sodium chloride and put it in some water and stir it up. Does that dissolve? Okay, check. Let's try sodium iodide. Put that in water. Does that dissolve? Check, yes. Silver chloride? Nope, that doesn't dissolve. And so they tried all these different things and then looked for patterns. So this is the list of solubility rules for ionic compounds in water. So who's going to ask the question? Do we have to memorize that? Yeah, thanks. Yes. Yes, you do. It's really not as bad as it looks. So let's talk about how you use this table. In the top, these are compounds. Compounds containing these ions are generally soluble. So if it's got one of these ions in it, it's probably soluble, except, so there's a list of exceptions over here, and this is what looks kind of complicated. But the way we're going to use this is we're always going to start at the top, and we're going to go down. So if I see that my compound has lithium in it, it doesn't matter what the other ion is, that compound is soluble, because this one has no exceptions. So let's say I had silver chloride. So I'm looking here, I don't see silver or chloride, I don't see silver or chloride. Here's chloride, and I have to go over here to see if there are exceptions. Well, there's 3 exceptions. Do we really need all these other words? No, we don't. So the exceptions are silver, mercury, or lead. And yeah, there are 2 different mercury ions, and one is soluble and one isn't. I will not try to trick you with that. So if you see mercury with chloride, I expect you to tell me it's insoluble. Up here, no exceptions. We could just have that blank because there's nothing there. There's no exceptions. Sulfate compounds are generally soluble except with these guys. So let's just get rid of the extra words. We got strontium, barium, lead, silver, and calcium. Strontium, barium, and calcium are group 2 metals. And the lead and the silver are the same as the ones up there. So then we get to the bottom half. These are generally insoluble, and we list the exceptions. So hydroxide and sulfide. Well, if it's paired with one of these, lithium, sodium, potassium, or ammonium, it's going to be soluble. Well, if we use this table by starting at the top and going down, let's say I've got lithium hydroxide. I'm trying to find out, is it soluble or not? I start at the top, I see lithium. It's soluble, done. I'm never going to get down here. So I don't really need this exception to be written out for me. That's just a bunch of words that looks confusing. So what are the exceptions? Well, the exceptions are calcium, strontium, and barium. Strontium, barium, calcium, same three guys as were exceptions up there. These guys made this insoluble. Down here, they make these guys soluble, but they're an exception. With sulfide, these are soluble. With hydroxide, these are slightly soluble. I say we don't need to worry about that difference. We're just going to go with soluble. So if I have strontium hydroxide, and I go through my list, I don't see strontium or hydroxide anywhere up here, and I get to hydroxide. And the exception, strontium's an exception. I know that that is at least slightly soluble. And then down here, carbonate and phosphate, the exceptions these have, again, are with those first ions. And so if we start at the top of the table, we are never going to get down there, so we really don't need to even think about that. Does that look a little better? Yeah. So what I've got here, my exceptions, I've got calcium, strontium, and barium. Calcium, strontium, and barium. So I'm just going to get rid of this strontium, barium, and calcium. And then I've got lead and silver. I don't know why they chose to do it in a different order, but it's the silver and the lead. So these two are almost identical to this one, and these three are the same as the exception down there. It's really not that bad. So the way you learn this is whenever you need to predict solubility, you try to remember, try to picture this chart in your head going down the list, and the more examples you do, the more you'll remember it. So you try to do it without looking at the table and then check and see if you're correct. Okay, let's practice. Predict whether each compound is soluble or insoluble. So nickel sulfide, insoluble. So we think about the chart, and up at the top there's the alkali metals and ammonium, and there was nitrate and acetate and the halides, and there was sulfate, and sulfide is in the bottom. Sulfide is insoluble with exceptions. Nickel wasn't an exception to anything, right? So this one's insoluble. How about magnesium phosphate? Was magnesium in the top anywhere? No. Phosphate's in the bottom. When we get down there, by the time we've gotten down there, there's no exceptions. So this is also insoluble. Let's go back and look at it. So up at the top there's nothing about magnesium. And I get down to the bottom, can't use my pointer. Get down here with the phosphate. The only exceptions are those guys way at the top. So magnesium isn't one of them. So that's insoluble. Lithium carbonate, soluble. Because lithium is in that first line. That first line is alkali metals, lithium, sodium, potassium, and then our weird friend ammonium. And those compounds are always soluble. How about ammonium chloride? Soluble. Again, you see NH4, it's soluble. No exceptions. Any questions?